Voyager 1 is more than 23 billion kilometers from Earth, traveling through interstellar space where temperatures hover just above absolute zero. It has spent nearly half a century exposed to radiation, vacuum, and cold more extreme than any environment humans can reproduce for comparable lengths of time. By all intuitive expectations, a machine built in the early 1970s should have failed long ago. Yet Voyager still communicates with Earth. It still receives commands, transmits data across billions of kilometers, and generates enough power to operate critical systems. Its survival is one of the most remarkable engineering achievements in human history. Understanding how Voyager continues to function begins with correcting a common misconception about space itself. Most people imagine space as a place that instantly freezes anything exposed to it. In reality, cold in space behaves very differently from cold on Earth. The physics of heat transfer in a vacuum is the key to understanding how a spacecraft can survive for decades in the darkness between the stars. What cold in space actually means. Cold, as experienced by a human being on Earth, is not primarily a property of the environment's temperature. It is primarily a property of heat transfer rate. When you stand outside on a January morning and feel cold air cutting through your jacket, what you are physically experiencing is the rapid removal of thermal energy from your skin by a mechanism called conduction. Air molecules, moving at speeds determined by the air temperature, collide with the molecules of your skin. Each collision transfers some kinetic energy from your skin to the air. Billions of collisions happen every second across every square centimetre of exposed skin. The cumulative effect is a steady, rapid drain of thermal energy from your body. The faster this drain occurs, the colder you feel. This is why wind makes cold feel colder. Wind does not lower the air temperature. It replaces the air immediately adjacent to your skin, which has been slightly warmed by previous collisions, with fresh cold air carrying full thermal gradient. More collisions per unit time means faster heat removal, means greater perceived cold. This is also why wet cold is more severe than dry cold at the same temperature. Water conducts heat from skin approximately 25 times faster than air does. The same thermometer reading feels dramatically colder when you are wet, because the rate of heat removal is 25 times higher. The critical variable in all of these terrestrial cold experiences is molecular density. Cold hurts because there are an enormous number of molecules to carry heat away. At sea level on Earth, 1 cubic centimetre of air contains approximately 2.7 times 10 to the 19th power molecules, or 27 quintillion molecules, each capable of conducting heat away from any warmer object they contact. This density is what gives Earth's cold its bite. In the interstellar medium where Voyager 1 currently travels, the particle density is approximately 1 atom per cubic centimetre, not 27 quintillion. 1. The difference between these two numbers is roughly 19 orders of magnitude, a factor of 10 billion billion. At this density, conductive heat transfer from a spacecraft to the surrounding environment is so negligible as to be effectively non-existent. There are essentially no molecules present to carry heat away from the spacecraft's surface. The mechanism that makes cold dangerous on Earth does not operate in any meaningful way in interstellar space. This is the central physical fact that explains Voyager 1's survival. Deep space is not cold in the way that winter is cold. It does not aggressively strip heat from anything placed within it. It is instead a passive environment that waits for heat to radiate away through the only mechanism available in a vacuum: electromagnetic radiation. Every object with a temperature above absolute zero emits electromagnetic radiation. This is thermal radiation, and it is described by the Stefan-Boltzmann law, which states that the power radiated per unit area of a surface is proportional to the fourth power of the absolute temperature. For an object at room temperature, this radiation is primarily in the infrared portion of the electromagnetic spectrum, invisible to the human eye, but measurable with suitable instruments. This is the mechanism by which objects cool in space. They radiate infrared photons outward in all directions, and if no corresponding radiation arrives from the environment to replace what is lost, the object gradually cools. The key word in that description is gradually. Radiative cooling is inherently slow compared to conductive cooling. A cup of coffee cooling on a desk on Earth loses its heat primarily through convection and conduction to the surrounding air. In a vacuum, the same cup can only cool by radiation, and the cooling rate drops dramatically. This is the physics behind the thermos bottle. The vacuum jacket in a thermos eliminates conductive and convective heat transfer, leaving only radiation, which is slow enough that coffee remains hot for hours rather than minutes. Voyager 1 is, in a very real physical sense, a sophisticated thermos. It is designed to lose heat slowly enough that the heat generated internally by its power source and electronics can maintain the spacecraft within operational temperature ranges despite the theoretically extreme cold of the surrounding environment. The deep cold of interstellar space is not an enemy fighting to freeze the spacecraft. It is an absence, a thermal sink that pulls at Voyager's warmth slowly and continuously. An absence that Voyager's engineers accounted for precisely and designed against successfully. Understanding this distinction between active cold, which attacks through molecular contact, and passive cold, which simply waits for radiation to drain warmth away, is the foundation of understanding everything that follows about how Voyager has survived. The plutonium heart, RTGs, and their physics. Voyager 1 does not carry solar panels. This was not an oversight or a limitation of 1970s technology. It was a deliberate engineering decision based on a clear understanding of where the spacecraft was going and what the solar environment would be at its destinations. The inverse square law of light intensity states that the intensity of light from a point source decreases in proportion to the square of the distance from that source. At Jupiter's orbital distance, approximately 5.2 astronomical units from the Sun, sunlight is already 27 times weaker than at Earth. At Saturn's distance of approximately 9.5 astronomical units, it is 90 times weaker. In the interstellar medium at Voyager's current distance of roughly 160 astronomical units, sunlight is approximately 25,600 times weaker than at Earth. Solar panels of any practical size would be entirely useless at these distances. Instead, Voyager 1 is powered by 3 radioisotope thermoelectric generators, or RTGs. Each RTG consists of a core of plutonium-238 dioxide pellets surrounded by thermoelectric conversion materials, all enclosed in a protective casing designed to survive both the space environment and potential launch accident scenarios. The RTGs are mounted on a boom extending from the main spacecraft bus, positioned to distance their radiation and heat from the sensitive scientific instruments. The operating principle of the RTG is elegant in its simplicity. Plutonium-238 is a radioactive isotope that decays by emitting alpha particles, which are helium-4 nuclei stripped of their electrons. As each alpha particle is emitted, it carries kinetic energy that is deposited as heat in the surrounding material through collisions with neighboring atoms. This radioactive decay cannot be switched off, cannot be accelerated, and cannot be slowed. It proceeds according to the exponential decay law determined by the isotope's half-life, which for plutonium-238 is approximately 87.7 years. The decay releases heat continuously, day and night, with or without sunlight, with or without any external energy input, in any environment anywhere in the universe. This heat is then converted to electricity through the Seebeck effect, the physical phenomenon by which a temperature difference across certain materials generates an electrical potential. The thermoelectric elements in the RTG, made from silicon-germanium alloys, have one end in thermal contact with the hot plutonium core and the other end exposed to the cold space environment. The temperature difference between these two ends drives electrons through the circuit, generating usable electricity. The efficiency of this conversion is low, approximately 5 to 6%, which means the vast majority of the heat produced by the plutonium is released into the spacecraft as waste heat rather than being converted to electricity. This low efficiency is not a flaw in the design, it is a feature. The waste heat that the thermoelectric conversion does not capture is thermal energy deposited into the spacecraft structure, warming it against the cold of space. At launch in 1977, Voyager 1's 3 RTGs together produced approximately 470 watts of electrical power. This is a modest number by everyday standards, roughly equivalent to the power consumed by 4 or 5 incandescent light bulbs. But it was sufficient for a spacecraft designed with extreme power efficiency in mind, in which every circuit, every instrument, and every subsystem was optimized to perform its function on a minimal power budget. The thermal output of the RTGs was substantially higher than the electrical output. At the 5 to 6% conversion efficiency, for every watt of electricity produced, approximately 16 to 18 watts of heat were released. At launch, the combined thermal output of all 3 RTGs was therefore approximately 2,500 watts, essentially a 500-watt space heater built into the spacecraft and running continuously. This thermal output, distributed through the spacecraft structure, was the primary mechanism keeping Voyager's components above their minimum operating temperatures in the years following launch, when it was already moving through the cold outer solar system. Plutonium-238 has a half-life of 87.7 years, meaning that every 87.7 years, half of the remaining plutonium atoms have decayed and are no longer contributing to heat output. The practical consequence is that the RTG power output declines continuously over the mission's life. The rate of decline is approximately 4 watts of electrical power per year and approximately 65 watts of thermal power per year. By 2026, after 49 years of operation, the electrical output has fallen to approximately 220 to 240 watts, roughly half the launch value. The thermal output has similarly decreased. This ongoing decline in power output has been the defining constraint of Voyager 1's operational lifetime since the planetary encounter phase ended and the spacecraft entered its interstellar mission phase. Every management decision, every instrument shutdown, every heater deactivation has been driven by the need to allocate the diminishing power output among competing demands, with the transmitter and attitude control systems receiving highest priority because without them, the spacecraft cannot communicate with Earth regardless of what its instruments are measuring. Multi-layer insulation, the thinnest armor in the universe. The second major component of Voyager's thermal survival strategy is its insulation system. The multi-layer insulation, or MLI, that covers most of the spacecraft's external surfaces is one of the most effective thermal insulators ever engineered, and it achieves this effectiveness through principles that seem counterintuitive until the physics is understood. Ordinary thermal insulation, the fiberglass bats in a house wall or the foam in a camping cooler, works primarily by trapping air. Air is a poor thermal conductor relative to solids, and trapping it in small pockets prevents the convective circulation that would otherwise carry heat through the material. The insulating value of these materials depends almost entirely on the trapped air. In space, where there is no air, this mechanism does not function. Foam insulation in a vacuum has almost no insulating value because the air that makes it effective is gone. MLI insulation works on entirely different principles that are specifically suited to the vacuum environment of space. A typical MLI blanket consists of many individual layers, often 20 or more, of very thin aluminized plastic film. Each layer is only a few micrometers thick, far thinner than a human hair. The layers are separated from each other by spaces that prevent direct thermal contact between adjacent layers. In Voyager's construction, both Mylar and Kapton films were used, and the layers were crinkled or embossed rather than flat, so that adjacent layers touch only at their raised points rather than across their full surfaces. The insulating mechanism operates through two physical effects. First, each metallic layer is highly reflective in the infrared. When infrared radiation from the warm interior of the spacecraft reaches the first MLI layer, a large fraction of it, typically 95% or more, is reflected back toward the interior rather than passing through. The small fraction that does pass through encounters the next layer, where most of it is again reflected. After passing through 20 or more such layers, the fraction of the original radiation that has made it through the complete blanket is reduced to a tiny percentage of the original. The insulation is effective because it repeatedly reflects radiation back toward the heat source rather than absorbing it and transmitting it outward. Second, the tiny contact points between adjacent layers where the crinkled films touch create extremely high thermal resistance. Even if some heat conducts through these contact points rather than radiating across the gaps, the contact area is so small and the thermal path so tortuous that conductive transfer through the MLI is negligible compared to the radiative transfer that the reflective layers suppress. The result is a thermal blanket that can achieve effective thermal conductivity hundreds of times lower than the best conventional insulators at negligible mass. Voyager's MLI blankets together weigh only a few kilograms but provide thermal protection that would require tens of centimeters of conventional insulation to approach. For a spacecraft where every gram of mass requires propellant to launch and where the available power for heating is already severely limited, this mass efficiency was not merely convenient. It was essential. The engineering challenge of the MLI design was not just achieving high insulating efficiency in deep space. It was designing a blanket system that could handle the dramatically different thermal environments Voyager would encounter across its mission. When Voyager 1 flew past Jupiter at a distance of approximately 350,000 kilometers in March 1979, it was bathed in Jupiter's intense radiation environment and was far closer to the Sun than it would later be. The RTGs were running at full power. The spacecraft had to be prevented from overheating as much as from freezing. The MLI had to be part of a thermal management system that could operate successfully across this entire range. The solution involved combining MLI blankets with thermal control louvers, which are adjustable vents in the spacecraft's surface that can open or close to regulate heat dissipation, and with the careful orientation of reflective and absorptive surfaces. Some surfaces were designed to radiate heat outward efficiently for temperature control during the warm inner solar system phase. Others were designed to retain heat for the cold outer solar system phase. The thermal design was a balance between competing requirements that had to function correctly across the entire planned mission duration without any possibility of physical maintenance or adjustment after launch. The thermal architecture of Voyager, engineering against the void. Understanding Voyager's thermal survival requires appreciating the spacecraft as an integrated thermal system, rather than simply a collection of components with insulation applied to them. The placement of every heat-generating component, the routing of every cable, the orientation of every surface, and the choice of materials for every structural element were all considered in the context of their thermal implications. The RTGs represent both the primary heat source and a potential thermal hazard. Mounted on a boom extending approximately 3 meters from the main spacecraft bus, they are physically separated from the sensitive scientific instruments that a strong radiation field or excessive heat could damage. This separation also means that the substantial heat they generate, approximately 2,500 watts at launch, must be managed so that the right amount reaches the spacecraft interior, keeping it warm, while excess heat is vented to space to prevent overheating during the warm early mission phase. The spacecraft electronics, housed in the central bus compartment, are the primary thermal load requiring protection from cold. Electronic components lose efficiency and eventually fail at low temperatures. Capacitors change their electrical characteristics. Battery chemistry slows and eventually stops. Lubricants in any mechanical components become viscous and eventually solid. The minimum operational temperatures for the various electronic components aboard Voyager range from approximately -35 degrees Celsius for some components to higher limits for others. Maintaining the interior electronics compartment above these limits across the entire mission required both the active heat input from the RTGs and the passive thermal retention of the MLI system. The thermal mass of the spacecraft also plays a role in temperature stability. Thermal mass refers to the capacity of a material to absorb and store heat. A material with high thermal mass changes temperature slowly when heat input or output changes. Voyager's structural elements, primarily aluminum alloys, have moderate thermal mass that helps buffer the spacecraft against short-term temperature fluctuations. When the power output of a heater is reduced, the structural thermal mass means the temperature drops slowly rather than immediately, providing time for thermal management adjustments. The cables connecting the RTGs to the spacecraft bus are both electrical conductors and thermal pathways. Heat conducted along these cables from the warm RTGs to the spacecraft interior provides a useful supplementary heating effect, supplementing the RTG waste heat that radiates from the RTG housing through the spacecraft structure. Managing the thermal conductance of these cables, ensuring they conduct enough heat to help warm the spacecraft without conducting so much that the RTGs are cooled below their optimal operating temperature range, was a specific aspect of the thermal design. The scientific instruments, distributed around the spacecraft on booms and on the scan platform, each had their own thermal requirements. Many instruments contained optical elements, electronic detectors, or mechanical components with temperature-sensitive characteristics. Some required active heating to maintain calibration across the temperature range of the mission. Others were designed to operate across a wide temperature range without adjustment. The thermal design of each instrument was integrated with the overall spacecraft thermal design to ensure that the instrument's operational requirements could be met without exceeding the available power budget for heating. As the mission has progressed and power has declined, the operational temperature ranges of various components have become increasingly important constraints. Several heaters for non-essential components and scientific instruments have been turned off as the power budget tightened, allowing those components to cool to ambient spacecraft temperature. In some cases, the temperature of deactivated components is below their operational range, meaning they could not be reactivated even if power were available. This progressive narrowing of the operational envelope is a direct consequence of the plutonium decay in the RTGs and has been managed by NASA with careful prioritization of the systems most essential to mission continuity. The heliopause crossing and its thermal implications. In August 2012, after 35 years of continuous travel, Voyager 1 crossed the heliopause, the boundary between the heliosphere and interstellar space. This crossing was not merely a milestone in distance, it was a transition into a genuinely different physical environment with different thermal characteristics that posed new challenges for the spacecraft's survival. The heliosphere is the region of space dominated by the solar wind, a continuous outflow of charged particles from the Sun that creates a bubble of solar influence extending far beyond the orbits of the planets. Within the heliosphere, the plasma environment, while extremely tenuous, is shaped by solar activity. The solar wind itself, travelling at several hundred kilometres per second, carries energy outward from the Sun. The interplanetary magnetic field, wound into a spiral pattern by the Sun's rotation, fills the heliosphere with a structured electromagnetic environment. Even at the distances Voyager travelled within the heliosphere, the spacecraft was in a physical environment defined by solar output. The interstellar medium beyond the heliopause is different in character. It is the material that fills the space between stellar systems, a diffuse mixture of gas and dust at a density of approximately 1 atom per cubic centimetre, compared to approximately 5 to 10 particles per cubic centimetre in the outer heliosphere near the heliopause. The plasma temperature in the outer heliosphere, measured by the thermal motion of its constituent particles, is actually very high, in some regions several 100,000 degrees Kelvin. This counterintuitive fact reflects the extreme tenuousness of the plasma. The individual particles are very energetic, but there are so few of them that they transfer essentially no heat to anything they contact. Temperature in this context describes the energy of individual particles rather than the capacity to heat macroscopic objects. Beyond the heliopause, in the local interstellar medium, the particle temperature is lower, but the density remains equally negligible. The thermal environment for Voyager changed at the crossing, not because of a dramatic temperature shift in the surrounding medium, which is irrelevant at these particle densities, but because the electromagnetic and particle radiation environment changed character from solar-dominated to galactic-dominated. The galactic cosmic ray environment in interstellar space is measurably different from that within the heliosphere. The heliosphere provides some shielding against low-energy cosmic rays, which are deflected or absorbed by the solar wind and interplanetary magnetic field. Beyond the heliopause, this shielding is absent, and Voyager's instruments detected a significant increase in the flux of low-energy cosmic rays immediately after the crossing. These cosmic rays carry energy that is deposited in the spacecraft's electronic components and structural materials through ionization and nuclear reactions, a form of radiation damage that has been accumulating throughout the mission. For Voyager's thermal management, the crossing into interstellar space was significant, primarily because it removed the spacecraft from any remaining thermal environment connected to solar output. Within the heliosphere, even at 100 or more astronomical units from the Sun, trace solar influence persisted. Beyond the heliopause, Voyager is entirely dependent on its own internal heat generation for warmth, with the thermal sink of interstellar space waiting patiently around it for any heat that radiates away. The RTGs continue to provide that heat, but their declining output makes the balance increasingly precarious. The instruments that detected and characterized the heliopause crossing were themselves thermally sensitive. The plasma wave science instrument and the magnetometer, which provided the primary evidence for the crossing, operate on electronic components that must be maintained within operational temperature ranges. After the crossing, several heaters that had been providing supplementary warmth to these instruments were turned off as part of the power management program, allowing the instruments to operate at lower temperatures closer to their minimum operational limits. Each heater deactivation represented a calculated risk, accepting higher probability of thermal damage to the instrument in exchange for extending the operational life of the overall spacecraft by conserving power. What 49 years have done to the spacecraft, a machine that has operated continuously for 49 years in the most hostile environment accessible to human technology, bears the marks of that experience in ways that go beyond simple aging. Voyager 1 has been subjected to radiation, thermal cycling, micrometeorite impacts, the gravitational stresses of planetary flybys, and the electromagnetic environment of interstellar space for longer than most of the people who currently work on the mission have been alive. Understanding what this means for the spacecraft's current condition requires looking at how each of these environmental factors has affected the components they act on. Radiation damage is the most pervasive and the most insidious. The cosmic rays and energetic particles Voyager has encountered throughout its journey interact with the electronic components in the spacecraft through several mechanisms. Ionizing radiation passing through semiconductor materials can create electron hole pairs that alter the electrical characteristics of transistors and integrated circuits. High-energy particles can cause single-event upsets, brief glitches in which a single particle hit flips a bit in memory or a register. Cumulative displacement damage occurs when particles displace atoms from their positions in crystal lattices, gradually degrading the performance of semiconductor devices. Over 49 years, the accumulated dose has exceeded the original radiation tolerance specifications of some components. The effects are not always immediate or catastrophic. Many radiation damage effects are gradual, manifesting as slow drift in component parameters rather than sudden failures. The engineers at NASA's Jet Propulsion Laboratory monitor the spacecraft's performance parameters continuously, watching for signs of radiation-induced degradation and updating their models of the spacecraft's current state accordingly. When a component behaves unexpectedly, the first interpretation is often radiation damage rather than mechanical failure, because radiation damage is the expected long-term degradation mode for electronics in this environment. Thermal cycling has also affected the spacecraft structure. Every time Voyager moves between environments with different thermal characteristics, every time a heater switches on or off, every time power consumption in a circuit changes, the temperature of the affected components changes slightly. These temperature changes cause thermal expansion and contraction in every material. The cumulative effect of millions of small thermal cycles over 49 years has stressed the structural connections between components, the solder joints connecting electronic components to circuit boards, and the fasteners holding structural elements together. Materials in space, without the protective effects of Earth's atmosphere, do not corrode, but they do undergo slow mechanical changes from the accumulated thermal stresses. The mechanical actuators in the spacecraft, primarily the attitude control thrusters that maintain Voyager's orientation in space, have been used continuously for 49 years. Each thruster firing is a tiny mechanical event, a valve opening and closing to release a precisely controlled pulse of hydrazine propellant. After billions of such events, the valves accumulate wear. The hydrazine fuel, stored in the spacecraft's tanks throughout the mission, gradually decomposes in a slow chemical reaction that reduces the effective fuel supply and produces decomposition products that can contaminate the thruster system. The reserves of hydrazine remaining are uncertain, but their finite quantity sets a limit on how long attitude control can be maintained regardless of what happens to the electrical power supply. In 2023, a critical failure and recovery event illustrated how precarious Voyager's situation has become. In late July of that year, a faulty command caused the spacecraft's antenna to rotate 2 degrees away from its pointing toward Earth. The communication link was lost. For 2 weeks, engineers at JPL worked to restore contact, ultimately using a sequence of commands broadcast toward Voyager's estimated position and relying on the spacecraft's own fault protection software to detect the communication gap and initiate a recovery procedure. The recovery succeeded, and contact was restored. But the incident demonstrated that at Voyager's distance, with its declining power and aging systems, any significant anomaly carries a real risk of permanent mission loss. The 2023 anomaly also exposed a maintenance challenge that has no precedent in human spaceflight. Voyager 1 runs software and hardware developed in the early 1970s, maintained by a team that must understand 50-year-old engineering documentation to interpret the spacecraft's behavior. The engineers who originally designed the systems have largely retired or died. Their knowledge exists in the documentation they left behind, which is comprehensive but cannot fully substitute for direct experiential knowledge of the design decisions that were made and the reasons they were made. Every year that passes, the challenge of maintaining institutional knowledge about Voyager's idiosyncrasies becomes more difficult. The power budget, managing a dying resource. The operational management of Voyager 1 since it entered its extended mission phase has been fundamentally an exercise in power budget management. Every capability the spacecraft possesses, every instrument that collects data, every heater that keeps a component warm, every computer cycle that processes a command or formats a data packet consumes electrical power from a fixed and continuously declining supply. The mission team's job has been to allocate this declining resource among competing demands, with the explicit goal of maximizing scientific return for as long as possible before the power runs out entirely. At launch, the 470 watts of electrical output from the RTGs was distributed among the spacecraft's systems according to a power allocation plan developed well before launch. The scientific instruments collectively consumed a significant fraction of the available power, with the remainder split between the spacecraft bus systems, communications, attitude control, and heaters. As the mission progressed and the power output declined, this allocation has been revised repeatedly, each revision involving the deactivation of one or more systems to free power for higher priority functions. The cameras that provided the iconic images of Jupiter, Saturn, Uranus from the extended Voyager 2 mission and Saturn's moons were turned off on Voyager 1 in April 1998. The logic was straightforward. Voyager 1 had completed its planetary encounter objectives, was now travelling through a region of space with no target suitable for optical imaging, and the power consumed by the imaging system could be better used for other purposes. The science instruments capable of measuring the interstellar medium, the magnetometer, the plasma wave science instrument, the cosmic ray subsystem, and the low energy charged particle instrument provided far more valuable data in the spacecraft's new environment. The prioritization of science instruments over non-essential subsystems has continued throughout the mission. As of 2026, the number of active science instruments on Voyager 1 has been reduced significantly from the original complement. In 2024 and 2025, JPL engineers faced particularly difficult decisions about which instruments to deactivate, driven by the power budget falling below the level needed to sustain all remaining active systems. The plasma wave science instrument and the magnetometer, which together provide the most scientifically valuable measurements of the interstellar medium, have been prioritized for retention as long as possible. Heater management has become equally critical. The spacecraft carries numerous small electric heaters designed to maintain components above their minimum operational temperatures. Some of these heaters serve essential functions, keeping the hydrazine fuel from freezing in the thruster lines, maintaining the communications electronics above their minimum operational temperature, keeping the attitude control computer within its functional range. Others are less essential, serving redundant systems or components that are no longer operational. As power has declined, less essential heaters have been turned off, allowing the components they served to cool below their operational ranges. This is an irreversible decision in most cases. Once a component has been allowed to cool below a certain temperature threshold, particularly in the case of certain lubricants or electrochemical systems, it cannot be returned to operational status even if power were later available. The engineering team monitors the thermal state of the spacecraft through temperature sensors at various points throughout the structure. These sensors provide data that is included in the engineering telemetry transmitted with every science data packet. The temperature readings allow the team to confirm that critical components remain within operational ranges and to identify any unexpected thermal trends that might signal a developing problem. When the readings approach the operational limits of a critical component, the team must choose between accepting the risk and conserving power, or activating a heater to move the component back within its safe range, consuming additional power in the process. This is the day-to-day reality of operating Voyager 1 in 2026, a continuous negotiation between the competing demands of science, survival, and power conservation, conducted across a communication delay of over 22 hours each way, with a spacecraft that gets slightly less capable every year as its plutonium heart beats a little more slowly, and the margin for error continues to narrow. The communications link across 23 billion kilometers. The signal that Voyager 1 transmits back to Earth travels 23 billion kilometers before reaching the receiving antennas of the Deep Space Network. At the speed of light, that journey takes approximately 22 hours and 21 minutes each way. A command sent from JPL this morning will not reach the spacecraft until tomorrow afternoon. Any response will not be received until the following day. Every interaction with the spacecraft operates on a 44-hour round-trip minimum. The signal itself is extraordinarily faint by the time it arrives. Voyager's transmitter operates at approximately 23 watts of radio frequency power, roughly the power of a standard household light bulb. This signal spreads outward in all directions as it travels, its power density decreasing with the square of the distance. By the time it arrives at Earth, after travelling 23 billion kilometres, the signal power at any receiving antenna is approximately 10 to the negative 17 watts or 100 femto watts. A femto watt is 10 to the negative 15 watts. The signal carrying humanity's farthest conversation is so weak that receiving it requires the largest antennas on Earth, the most sensitive receivers available, and sophisticated signal processing to extract meaning from the noise. The Deep Space Network, operated by NASA through JPL, consists of 3 complexes located approximately 120 degrees of longitude apart around Earth's circumference to ensure that at least one complex always has Voyager 1 in view above its horizon. The complex at Goldston, California, serves the Pacific sector. The complex near Madrid, Spain, serves the Atlantic and European sector. The complex near Canberra, Australia, serves the Southern Hemisphere. Each complex contains multiple antenna dishes of different sizes, with the largest measuring 70 metres in diameter. The 70-metre antennas are the workhorses of deep space communication. Their enormous collecting area captures the maximum possible signal power from Voyager's transmissions. The receivers attached to these antennas are cooled to near absolute zero using liquid helium to minimize thermal noise, which at room temperature would overwhelm the faint signal from Voyager. Even with these precautions, the data rate achievable from Voyager 1 is extremely low, approximately 160 bits per second, under the best conditions. For comparison, a typical home internet connection transfers data at millions of bits per second. Voyager communicates at a rate that would have been considered slow even for a telephone modem in the 1980s. At 160 bits per second, transmitting a single image of the kind Voyager's cameras captured during the planetary encounter phase, an image containing roughly 800 by 800 pixels at 8 bits per pixel, would take approximately 3,200 seconds, or nearly an hour. This is why the cameras were turned off long after the planetary encounters. Their data product, high-resolution images, simply could not be transmitted efficiently at the data rates achievable from Voyager's current distance. The science instruments that remain active produce data streams compatible with the available bandwidth, magnetic field measurements, particle count rates, and plasma wave amplitudes that can be transmitted efficiently at 160 bits per second. The pointing requirement for the communication link is severe. Voyager's high-gain antenna at the 3.7-metre diameter parabolic dish must be pointed within fractions of a degree of Earth's position for the communication link to be maintained. At 23 billion kilometres, the slightest misalignment sends the narrow antenna beam well past Earth's position. Maintaining this pointing across 49 years has been one of the primary demands on the spacecraft's attitude control system, which uses a combination of celestial navigation references, primarily the Sun and the bright star Canopus, and small thruster firings to keep the antenna aimed at home. The thruster system that maintains this pointing has been in use for 49 years. The hydrazine fuel it consumes is finite. The valves it uses accumulate wear with every firing. The engineers at JPL continuously monitor the thruster performance and efficiency, looking for signs of degradation that would signal an approaching end to the attitude control capability. If the thrusters fail before the power runs out, the spacecraft will gradually drift off its Earth-pointing orientation, and the communication link will be lost, even though the transmitter continues to operate. This would be a communication failure rather than a power failure, but the result for the mission would be the same. What the spacecraft has discovered in the interstellar medium, the scientific return from Voyager 1's interstellar mission phase, has been substantial and in several ways surprising, revealing properties of the local interstellar medium that were not accurately predicted by pre-crossing models. This data justifies the effort devoted to maintaining the spacecraft's operation and provides context for understanding why the mission team has made the difficult power management decisions necessary to keep the science instruments operating. The heliopause crossing itself provided the first direct measurement of the boundary between the heliosphere and interstellar space. Models developed before the crossing had predicted that this boundary would be gradual and diffuse, a broad transition region rather than a sharp boundary. Voyager 1's data showed instead a relatively sharp transition. The magnetic field direction changed abruptly. The flux of low-energy cosmic rays increased sharply. The solar wind plasma essentially ceased. These measurements revealed that the heliopause is a more defined boundary than expected, a finding that required revision of standard heliospheric models. In the years following the crossing, the plasma wave science instrument detected oscillations in the surrounding plasma that allowed the electron density of the interstellar medium to be directly measured for the first time. Before Voyager's crossing, interstellar medium electron density in the solar neighborhood had been estimated from indirect methods, including the dispersion of radio signals from distant pulsars. Voyager's direct measurement confirmed and refined these estimates, providing a benchmark value for the local interstellar medium that will be used to calibrate future measurements. The magnetic field measurements from the magnetometer revealed unexpected structure in the interstellar magnetic field near the heliopause. Rather than a uniform field aligned with the expected large-scale galactic magnetic field direction, the measurements showed variations and distortions consistent with the local interstellar magnetic field being influenced by the presence of the heliosphere itself. The heliosphere, it turns out, does not merely sit passively within the surrounding interstellar medium. Its magnetic field connects to and distorts the interstellar field in the region immediately surrounding it, creating a structured interaction zone that extends beyond the heliopause. These findings have direct implications for models of the heliosphere's protective function. The heliosphere shields Earth from a substantial fraction of the galactic cosmic ray flux, reducing the radiation environment in the inner solar system. The efficiency of this shielding depends on the properties of the heliospheric boundary and its interaction with the interstellar medium. Voyager's measurements have revealed that these properties are more complex than previously understood, suggesting that models of cosmic ray penetration into the inner solar system need to be revised. The data continue to accumulate. Each transmission from Voyager 1 carries measurements of the current magnetic field, current cosmic ray flux, and current plasma wave environment at the spacecraft's location, which changes by approximately 3.6 astronomical units per year as the spacecraft moves through the interstellar medium. The time series of these measurements, extending now more than a decade since the heliopause crossing, constitutes a unique scientific record of conditions in the local interstellar medium at a series of distances from the heliopause. This record cannot be replicated by any other current or planned instrument. Voyager and Newton's first law. The end of Voyager 1's operational life is not a distant or uncertain prospect. Based on the known rate of plutonium decay in the RTGs, the known power consumption of the spacecraft's remaining active systems, and the expected rate of future system shutdowns, the engineers at JPL have been able to construct reasonably precise projections of how many operational years remain. The projections suggest that the last science instrument will go dark sometime between 2025 and 2030. The transmitter itself may continue operating for a year or two after the last instrument shuts down, transmitting engineering telemetry with no science data, before its power supply too falls below the minimum operational level. The first signs of the final decline will be additional instrument shutdowns. As the power budget falls below the level needed to sustain all remaining active systems simultaneously, the mission team will face choices about which instruments to deactivate. These choices will balance the scientific value of the measurements each instrument provides, the power each instrument consumes, and the engineering state of each instrument. An instrument that is already partially degraded by radiation damage and consuming significant power might be deactivated in favor of one that is healthier and provides more valuable measurements per watt. Following the last instrument shutdown, the spacecraft will enter a phase of purely engineering telemetry, transmitting data about its own status, power levels, temperatures, attitude control performance, and the health of the transmitter and receiver. This data is less scientifically valuable than the interstellar medium measurements, but it provides information about the spacecraft's behavior in conditions of extreme age and extreme environment that has engineering value for future missions. Understanding how electronic components, structural materials, and mechanical systems behave after 50+ years in the interstellar environment will inform the design of future interstellar missions. The final transmission, when it comes, will likely not be dramatic. There will be no planned final message, no orchestrated goodbye. The transmitter's power output will slowly decline as the RTG output falls below the minimum operational level, and the signal received on Earth will gradually fade below the detection threshold of the Deep Space Network's receivers. Distinguishing the last real signal from background noise may be difficult, and the exact moment of final loss of signal may only be determined in retrospect after the team has waited long enough with no confirmed contact to conclude with confidence that the spacecraft has gone silent. After the final signal, Voyager 1 will continue travelling at approximately 17 kilometers per second, carrying its momentum through the interstellar medium indefinitely. Space contains no friction, no air resistance, no mechanism to slow a freely moving object. Newton's first law applies without qualification. An object in motion continues in motion until acted upon by an external force. The gravitational influence of passing stars will very slowly alter Voyager's trajectory over thousands of years. But the changes will be slight and gradual, and the spacecraft will continue moving roughly outward from the solar system for geological timescales. In approximately 40,000 years, Voyager 1 will make a close approach to the star Gliese 445, a red dwarf star approximately 17.6 light-years from Earth. The approach will not be a collision, but a pass at a distance of approximately 1.7 light-years, which will bring it closer to another stellar system than it has been since leaving our own. At this point, the spacecraft's transmitter will have been silent for nearly 40,000 years. The plutonium in the RTGs will have decayed to a small fraction of its original quantity. The temperature of the spacecraft structure will have equilibrated to approximately the temperature of the surrounding interstellar medium. The golden record attached to the spacecraft's exterior will be intact, its protective aluminum cover unchanged by the vacuum of interstellar space, carrying its encoded sounds and images of a civilization that built a machine capable of crossing to another star's neighborhood, even if it did so in silence and in the dark. The timescales involved extend far beyond anything normally considered in engineering. Most human-made objects are designed with operational lifetimes measured in years or decades. Even the most durable structures on Earth, stone monuments, pyramids, and ancient cities, survive only because they exist in environments that can be repaired, maintained, or partially protected from complete destruction. Voyager will receive no maintenance. No component will ever be replaced. No engineer will ever touch it again. Its future is entirely determined by the interaction between its materials and the physical environment of the galaxy. Over millions of years, microscopic impacts from interstellar dust will gradually erode exposed surfaces. Individual collisions will be insignificant, but their cumulative effect will slowly sandblast the spacecraft at atomic scales. The process is extraordinarily slow because interstellar space is so empty, yet geological time is extraordinarily long. Features machined into Voyager's surface today will eventually soften and degrade under countless impacts too small to observe individually. The spacecraft's most famous artifact, the Golden Record, was designed with these timescales in mind. The gold-plated copper disc carries sounds, music, images, and scientific information about Earth encoded in analog form. It was intended not as a practical communication device, but as a time capsule, a physical statement that a technological civilization once existed around a small star in the outer regions of the Milky Way. Long after Voyager's transmitters fail, the record will remain attached to the spacecraft, silently carrying its information through interstellar space. The probability that another civilization will ever encounter Voyager is extremely small. The distances between stars are vast, and the spacecraft occupies only a tiny volume within that immense emptiness. Yet the possibility is not zero. Over hundreds of millions of years, Voyager will pass through regions of the galaxy that do not currently exist in their present form. Stars orbit the galactic center. Stellar neighborhoods disperse and reform. Entire constellations change beyond recognition. The night sky seen from Earth today is a temporary arrangement, and Voyager will outlive it many times over. In that sense, Voyager's greatest achievement may not be scientific, but temporal. It is one of the few objects humanity has created whose journey will continue long after every nation, language, institution, and perhaps even our species has changed beyond recognition. The spacecraft will become an artifact of a civilization that exists only in history, still moving through the galaxy under the same laws of motion that launched it, carrying a record of a world that may no longer resemble the one that sent it. The engineers who keep a 49-year-old machine alive. The story of Voyager 1's survival is not only a story of physics and engineering decisions made in the early 1970s. It is equally a story of the people who have maintained the spacecraft's operation across 5 decades, navigating the compounding difficulties of declining power, aging systems, and the progressive loss of institutional knowledge about a spacecraft whose original designers are largely no longer working on it. The Voyager mission is managed from the Jet Propulsion Laboratory in Pasadena, California, by a small team of engineers and scientists who have dedicated careers to understanding and operating 2 spacecraft built before most of them were born. The team is small in part because of budget constraints, as the Voyager missions receive funding commensurate with their status as extended legacy missions rather than flagship active missions, and in part because the spacecraft's minimal power budget means there is relatively little operational complexity to manage on a day-to-day basis compared to a spacecraft with full instrument suites and high data rates. The central challenge facing the Voyager team is one that has no precise precedent in the history of space operations: maintaining institutional knowledge about a spacecraft across generational change. The engineers who designed Voyager 1 and oversaw its construction, launch, and planetary encounters were at the height of their professional careers in the mid-1970s. By the 1990s, many had retired. By the 2000s, most had left the program entirely. The engineering drawings, design documents, and operational procedures they created form the documentary record from which current operators must work. But documents cannot fully transmit the implicit knowledge of a system that builds up over years of direct experience. Certain aspects of Voyager's behavior are idiosyncratic, reflecting design choices made for reasons that may not be fully documented or may be documented in ways that require deep contextual knowledge to interpret correctly. When the spacecraft behaves unexpectedly, as it did during the 2023 antenna anomaly, and during earlier computer memory corruptions, the team must diagnose the problem from the telemetry data, compare the observed behavior to the documented expected behavior, and develop a response strategy that accounts for the spacecraft's age and degraded state. This diagnostic process depends on a thorough understanding of the spacecraft's design that becomes harder to maintain as the original designers become unavailable and as the spacecraft accumulates operational history that departs further from its original specifications. In 2023, when the antenna pointing anomaly occurred, the team's response demonstrated both the difficulty and the resourcefulness of operating an aged spacecraft at extreme distance. The problem was diagnosed as a garbled software command that had caused the spacecraft's flight computer to execute an incorrect sequence, rotating the antenna away from Earth. The fix required sending a precise command sequence to a computer running software last updated decades ago, using a programming interface whose documentation was written by people who had long since retired, transmitted to a spacecraft that could not acknowledge receipt for 22 hours after each command was sent. The recovery took approximately 2 weeks, with the team maintaining round-the-clock monitoring and carefully sequencing each command attempt to avoid compounding the problem. The successful recovery was a testament to the team's understanding of the spacecraft, but it also underscored how close to the operational edge Voyager 1 operates. A more severe software corruption, a failure of the redundant computer, or a misdiagnosis of the problem could have resulted in permanent loss of the communication link at any point during those 2 weeks. The team also faces the technical challenge of maintaining communication infrastructure that is itself aging. The Deep Space Network antennas that receive Voyager's transmissions are large, complex structures that require continuous maintenance and periodic upgrades to remain functional. The 70-meter antenna at the Goldstone complex in California, the Madrid complex in Spain, and the Canberra complex in Australia are indispensable to the mission. Without them, there is no link between Earth and Voyager, regardless of the spacecraft's operational state. Maintaining these antennas and the receiver systems attached to them involves balancing the needs of Voyager against the needs of other missions that also depend on Deep Space Network resources. In 2025, the Canberra 70-meter antenna underwent a scheduled maintenance period that required its temporary deactivation. During this period, contact with Voyager 1 was reduced to briefer windows using smaller antennas, limiting the data return and constraining the team's ability to send commands. These infrastructure constraints, entirely separate from the spacecraft's own declining capabilities, represent an additional dimension of the mission management challenge that will only become more complex as the spacecraft approaches its final operational years, the golden record, and what survives. Among the most enduring aspects of the Voyager 1 mission is the physical artifact that will survive longest after the spacecraft goes silent, the golden record. Attached to the spacecraft's exterior in a protective aluminum cover, the golden record is a 12-inch gold-plated copper disc encoded with sounds and images selected to represent Earth and its inhabitants. It was designed and assembled in 1977 under the direction of Carl Sagan, with the explicit purpose of providing a portrait of Earth to any extraterrestrial intelligence that might one day encounter the spacecraft. The record contains 115 images encoded in analog format, including photographs of Earth's geography, diverse human beings, animals, plants, and examples of scientific and mathematical knowledge. It contains greetings spoken in 55 human languages. It contains sounds of Earth, including rain, wind, thunder, waves, birds, whales, and a human heartbeat. It contains 90 minutes of music from diverse cultures and traditions. On the cover are engraved instructions for playing the record, diagrams showing the location of Earth relative to 14 known pulsars, and a sample of uranium-238, whose radioactive decay can serve as a clock indicating when the record was made. The golden record was not designed as a realistic communication device. Sagan and his colleagues were under no illusion that the probability of the record being found and read by an extraterrestrial intelligence was high. The value of the record, as Sagan described it, was as much in its creation as in any prospect of its reception. The process of deciding what to include, of determining what sounds and images and words best represented humanity, was an exercise in self-reflection that had a value for the civilization that undertook it regardless of any outcome. In purely material terms, the golden record is among the most durable artifacts humanity has created. Gold does not oxidize. Copper, protected by its gold plating, resists corrosion. Aluminum, forming the cover, develops a thin oxide layer that protects against further degradation. In the vacuum of interstellar space, with no atmosphere to support chemical weathering and no liquid water to enable electrochemical processes, these materials will remain essentially unchanged for timescales measured in geological epochs. The primary degradation mechanism for the record in interstellar space is micrometeorite impact erosion, in which tiny particles of dust collide with the record surface and slowly abrade it over millions of years. The rate of this erosion is low enough that the record is expected to remain substantially intact for at least 1 billion years. This creates a peculiar asymmetry between the record and the spacecraft that carries it. The spacecraft's electronic systems are failing, its power source is nearly exhausted, its transmitter will fall silent within years. But the physical disk it carries will still be travelling through the galaxy when the Earth's continents have rearranged themselves through plate tectonics, when the Sun has brightened enough to render Earth's surface uninhabitable, and when the Milky Way and Andromeda galaxies have begun their merger. The most fragile part of Voyager 1, the electronics, will fail first. The most durable part, the record, will outlast almost everything else humanity has built. The combination of the spacecraft and the record represents a specific kind of achievement, not the achievement of reaching a destination, because Voyager 1 will not meaningfully reach any specific destination within any human-relevant timescale, not the achievement of establishing communication, because the record is almost certainly never going to be found, but the achievement of making permanent, of fixing in physical form and launching into permanent motion, a representation of a civilization's existence at a specific moment in its history. Voyager carries humanity's fingerprint into the galaxy as a physical object, slower than light, colder every decade, but persistent in a way that no digital archive, no broadcast signal, no written record could match. The physics of permanent motion. When Voyager 1's transmitter finally falls silent, the spacecraft will not stop. This is not a poetic statement or a metaphor. It is a consequence of one of the most fundamental laws of physics, Newton's first law of motion, which states that an object in motion continues in motion at constant velocity unless acted upon by a net external force. In the interstellar medium, where Voyager travels, there are essentially no forces capable of slowing a spacecraft at its current velocity on any timescale shorter than geological. The primary forces that could slow Voyager are gravitational and resistive. Gravitational influence from distant stars tugs very gently on the spacecraft, but these gravitational forces, distributed roughly isotropically from all directions across the galaxy, produce a net effect that is vanishingly small on human timescales. Over thousands of years, the cumulative gravitational perturbations from the nearest star systems will very slightly alter Voyager's trajectory, but they will not appreciably slow it. The interstellar medium itself exerts a resistive force as its atoms and dust grains impact the spacecraft's forward face. At 17 kilometers per second, each impact deposits momentum in the forward direction, slowing the spacecraft imperceptibly. The interstellar medium at 1 atom per cubic centimeter is so sparse that the force from these impacts is extraordinarily small. Over thousands of years, the deceleration from interstellar medium resistance is negligible. Over millions of years, it remains extremely small. The spacecraft will effectively maintain its current velocity for timescales that dwarf the history of human civilization many times over. This permanence of motion is one of the most alien features of the spacecraft's future trajectory to human intuition. Human experience is dominated by the continuous braking effects of friction and air resistance. Objects set in motion slow down and stop unless additional force is continuously applied. The bicycle coasts to a halt. The ball rolling across the floor eventually stops. The car travelling down the highway requires engine power to maintain speed against air resistance. In these terrestrial contexts, motion is a transient state. Rest is the natural endpoint. In space, particularly in the interstellar void, where there is neither friction nor air resistance, motion is the permanent state. Rest is irrelevant. A spacecraft given a velocity in any direction will maintain that velocity indefinitely, deviating only under the influence of gravity. Voyager 1 received its velocity from the launch rocket, refined by gravitational assist maneuvers at Jupiter and Saturn, and it will maintain that velocity across timescales that are difficult to conceptualize. At 17 kilometers per second, Voyager 1 travels approximately 1.47 million kilometers per day, approximately 536 million kilometers per year, approximately 5.4 light hours per year. To travel one full light year at this speed requires approximately 17,600 years. The nearest star, Proxima Centauri, is 4.24 light years away. If Voyager 1 were pointed directly at Proxima Centauri, which it is not, it would arrive in approximately 74,600 years. In 40,000 years, it will make its closest approach to Gliese 445, passing at a distance of 1.7 light years. In 296,000 years, it will pass within 4.3 light years of another star. In millions of years, its trajectory will have been perturbed enough by stellar gravitational influences that prediction of its precise path becomes uncertain. In billions of years, it will be adrift in the stellar neighbourhood of the Milky Way, its trajectory shaped by the collective gravitational influence of the galaxy itself. Throughout this journey, the spacecraft will be dark, cold, and silent. Its electronics will have long since failed from radiation damage and the slow degradation of all materials across geological time. Its plutonium will have decayed to a small fraction of its original quantity, producing too little heat to warm anything. Its structural metals will have experienced billions of small thermal cycles, as the faint starlight they encounter slowly warms one face then another, as the spacecraft slowly tumbles without the attitude control system to maintain its orientation. But it will be moving, always moving, at 17 kilometers per second, a piece of Earth, launched by Earth, carrying Earth sounds and images, forever in motion through the galaxy that Earth calls home. The magnetic field measurements that changed everything. Among all the instruments Voyager 1 carries, the magnetometer is perhaps the most scientifically consequential for the interstellar phase of the mission. It measures the strength and direction of the magnetic field surrounding the spacecraft, and the measurements it has returned since the heliopause crossing have revealed a picture of the local interstellar magnetic field that differs significantly from what theorists predicted. Understanding what these measurements actually show and why they matter for the broader project of understanding Earth's galactic neighbourhood requires some background in how magnetic fields structure the interstellar environment. The Sun produces a magnetic field that extends throughout the heliosphere, carried outward by the solar wind as what is called the interplanetary magnetic field. As the solar wind flows outward from the Sun in all directions, while the Sun simultaneously rotates once approximately every 25 days, the interplanetary magnetic field wraps into an Archimedean spiral pattern, resembling the pattern of water from a spinning garden sprinkler. At the distances, Voyager 1 was travelling through the outer heliosphere. This spiral pattern was still detectable in the magnetometer data, though wound to very tight angles because of the large distances from the Sun. Pre-crossing models of the heliosphere predicted that as Voyager crossed the heliopause, it would transition from this solar-dominated magnetic field structure to the background interstellar magnetic field, a field whose direction and strength are set by the large-scale dynamics of the galaxy rather than by the Sun. The expected interstellar magnetic field in the solar neighbourhood had a direction that most models placed roughly in the plane of the Milky Way, roughly parallel to the galactic midplane. The expected magnitude was approximately 1 to 3 microgauss, an extraordinarily weak field by everyday standards, but measurable by the sensitive magnetometer Voyager carries. What the magnetometer actually found when Voyager crossed the heliopause was broadly consistent with these predictions in magnitude, but more complex in structure than anticipated. The field direction in the interstellar medium immediately beyond the heliopause showed variations that indicated the boundary region between the heliosphere and the interstellar medium is not a simple, clean interface where solar magnetic influence stops and galactic magnetic influence takes over. Instead, the boundary appears to involve significant interaction between the two field systems, with solar magnetic field lines connecting to and draping around the heliopause in ways that create a structured transition region with its own distinct field geometry. Voyager 1's magnetometer data from the first several years after the heliopause crossing revealed episodic oscillations in the magnetic field strength that corresponded to pressure pulses propagating outward from the Sun. When the Sun produces a large coronal mass ejection or a period of elevated solar wind activity, the pressure pulse travels outward through the heliosphere, and when it reaches the heliopause, can push the boundary outward and create waves in the interstellar medium just beyond the heliopause. Voyager's magnetometer detected these waves, allowing scientists to track the propagation of solar disturbances into interstellar space for the first time. These observations established that the heliosphere is not a static bubble. It breathes, expanding and contracting in response to the Sun's activity cycle. The heliopause is not a fixed boundary, but a dynamic surface that moves in and out by tens of millions of kilometers over the course of years in response to solar wind pressure variations. This dynamic nature of the heliosphere's boundary has implications for the shielding it provides against galactic cosmic rays. A more expanded heliosphere provides more shielding, while a more compressed heliosphere allows more cosmic rays to penetrate to the inner solar system. Voyager's measurements provide the first direct observational basis for quantifying these effects. Beyond the heliopause, the magnetic field measurements revealed a region of enhanced magnetic field strength that was not predicted by simple models. This region, sometimes called the wall of the heliosphere, appears to result from the compression and draping of interstellar magnetic field lines around the heliosphere as the solar system moves through the local interstellar medium at approximately 23 kilometers per second relative to the local standard of rest. As the heliosphere plows through the interstellar medium, field lines pile up in front of it and around its sides, creating a region of elevated field strength that forms a kind of magnetic wall surrounding the heliosphere. Voyager 1, travelling in a direction roughly upstream of the heliosphere's motion through the interstellar medium, has been sampling this wall region and the more undisturbed interstellar medium beyond it. The distinction between the wall region and the undisturbed interstellar medium is scientifically significant because the wall region's properties are partly determined by the heliosphere's presence, while the undisturbed medium represents the conditions the heliosphere exists within. Understanding both is necessary for constructing accurate models of how the heliosphere interacts with its galactic environment. Voyager 1 is the only instrument that has ever directly sampled either region, and each year of continued operation extends the baseline of this one-of-a-kind data set. The persistent hum, what Voyager heard in interstellar space. In 2021, researchers analysing data from Voyager 1's plasma wave science instrument published a finding that captured widespread public attention. The spacecraft had detected a persistent, faint hum in the interstellar plasma, a continuous low-frequency oscillation that represented the background electrical activity of the interstellar medium itself. This discovery, reported by Stella Ocker and colleagues at Cornell University, illustrated both the extraordinary sensitivity of the instruments Voyager carries and the genuinely alien character of the environment it now occupies. The plasma wave science instrument detects oscillations in the electric field of the surrounding plasma, specifically waves propagating through the charged particles of the interstellar medium. Before the crossing, this instrument had been monitoring the electromagnetic environment of the outer heliosphere, detecting waves generated by solar-wind interactions, shocks, and instabilities in the heliospheric plasma. After the crossing, it found a different environment, quieter in some respects, but punctuated by specific types of electromagnetic activity that provided new information about the interstellar medium's properties. The most scientifically valuable observations from the plasma wave science instrument in the interstellar phase have involved measurements of the electron density in the local interstellar medium. When a pressure wave from the Sun, generated by a coronal mass ejection or a period of enhanced solar wind, propagates through the heliosphere and impinges on the heliopause, it can excite plasma oscillations in the interstellar medium just beyond the boundary. These oscillations produce a detectable signal in the plasma wave instrument at a frequency called the electron plasma frequency, which depends only on the density of the surrounding electrons. By measuring this frequency, scientists can calculate the electron density directly. This direct measurement of electron density is more precise and more local than any previous measurement of this quantity. Before Voyager's crossing, electron density in the local interstellar medium had been estimated from the dispersion of radio pulses from distant pulsars. A pulse containing multiple radio frequencies arrives with different frequencies travelling at slightly different speeds through the ionized interstellar medium, and the amount of this dispersion integrated along the long path from the pulsar to Earth provides an average electron density along that path. This method is powerful, but gives an average over thousands of light years rather than a local measurement. Voyager's plasma wave data provides a measurement of the electron density within a few light hours of the spacecraft's current position, which is orders of magnitude more local and therefore more directly relevant to understanding the properties of the immediate solar neighbourhood. The persistent hum discovered by Ocker's team represents background plasma wave activity in the undisturbed interstellar medium between the episodic bursts associated with solar disturbances. This background activity, at a very low level compared to the bursts, appears to be an intrinsic property of the interstellar plasma itself, rather than a response to any specific external stimulation. Its existence and properties provide information about the physical state of the interstellar plasma that complements the density measurements from the burst-associated oscillations. The detection of this hum required careful analysis of the plasma wave instrument's data over extended periods, distinguishing the true interstellar signal from instrumental noise and from cosmic ray interference. The fact that the instrument retains sufficient sensitivity to detect a signal this faint, after 49 years of operation and cumulative radiation damage, speaks to both the robustness of the original design and the care with which the instrument has been operated. The plasma wave instrument was not designed to make measurements in interstellar space. It was designed for the planetary encounter phase to characterize the electromagnetic environment near Jupiter and Saturn. Its continued operation and scientific usefulness in the interstellar medium is a fortunate consequence of its sensitivity and the spacecraft's remarkable longevity. The scientific importance of these measurements extends beyond the immediate neighbourhood of Voyager itself. The interstellar medium is not empty space. It is a dynamic environment composed of gas, plasma, magnetic fields, cosmic rays, and dust distributed throughout the galaxy. Although extremely tenuous by terrestrial standards, its properties influence the formation of stars, the evolution of planetary systems, and the propagation of radiation across interstellar distances. Understanding its local structure is therefore important not only for heliophysics, but for astrophysics more broadly. Voyager's measurements have revealed that the local interstellar medium is considerably more structured than once assumed. Rather than a uniform sea of particles, it contains variations in density, magnetic field strength, and plasma conditions over relatively small distances. As Voyager continues outward, each new measurement samples a slightly different region of this environment, allowing scientists to construct an increasingly detailed picture of the galactic neighbourhood through which the solar system is currently moving. The spacecraft's observations have also provided a unique perspective on the heliosphere itself. Before Voyager crossed the heliopause, many theoretical models predicted different values for the density, pressure, and magnetic properties of the surrounding interstellar plasma. The direct measurements obtained after the crossing allowed these models to be tested against reality for the first time. In several cases, the results forced revisions to long-standing assumptions about the interaction between the solar wind and the interstellar medium. Perhaps most remarkable is the fact that these discoveries are being made by a spacecraft launched before the first personal computer, before the internet, before GPS navigation, and before most of the scientists currently analysing its data were born. The plasma wave instrument continues to return scientifically valuable observations from a region of space no other active spacecraft has ever entered. Every transmission arrives from farther away than the previous one, carrying information from an environment that remained entirely inaccessible throughout most of human history. In a broader sense, the faint interstellar hum detected by Voyager represents something unprecedented. For the first time, humanity is not merely inferring the properties of the space between the stars from distant observations. It is measuring them directly. The signal is extraordinarily weak, generated by a plasma so diffuse that billions of cubic meters contain less matter than a breath of air on Earth. Yet from that faint background oscillation, scientists can extract information about the density, structure, and behavior of the medium that fills the galaxy itself. The result is a subtle but profound shift in perspective. The space between the stars is no longer an abstract concept reconstructed from theory and remote observation. Through Voyager's instruments, it has become a place with measurable properties, detectable activity, and a physical reality that can be studied directly. The spacecraft is not simply travelling through interstellar space. It is allowing humanity to hear, for the first time, the quiet electrical activity of the galaxy beyond the Sun's protective influence. The engineers said goodbye more than once. One of the most humanly compelling aspects of the Voyager 1 story is the repeated experience of mission team members believing they were approaching the end of the spacecraft's useful life, only to see the mission continue for additional years or decades. This pattern has repeated itself across the mission's history, and each iteration has shaped the emotional and professional relationship between the team and the spacecraft in distinctive ways. The first major farewell came at the end of the planetary encounter phase. When Voyager 1 completed its flyby of Saturn in November 1980, and its trajectory carried it away from the planetary plane at a steep angle that precluded any further planetary encounters, the close of the primary mission was formally acknowledged. The cameras were still operational, the science instruments were largely functional, and the spacecraft was healthy. But the extraordinary images and data products that had defined the mission's public identity were largely complete. Many of the scientists and engineers who had devoted years to planning and executing the planetary encounters moved on to other missions or other phases of their careers. The remaining team made the transition to managing a very different kind of mission, one defined by long intervals of routine data collection punctuated by occasional discoveries from the slowly changing interstellar environment. The second major farewell period came in the 1990s and early 2000s as the power budget tightened and instrument deactivations became routine. Each time an instrument was turned off, members of the team who had spent years working with that instrument's data experienced a specific personal kind of loss. The plasma science experiment, which had characterized the solar wind throughout the planetary encounter phase, was turned off in 2007. The low-energy charged particle instrument, which had detected the charged particles accelerated by planetary magnetospheres and by the termination shock, was deactivated around the same period. Each shutdown was the result of careful analysis and deliberate decision-making, but that did not make the moment of deactivation less significant to the people who had worked with these instruments. Suzanne Dodd, who has served as the Voyager project manager since 2010, has spoken in interviews about the emotional complexity of managing the mission's decline. The team operates with full awareness that they are supervising the final years of spacecraft that will never be replaced, managing capabilities that once lost are gone permanently. The data each instrument generates is not merely scientifically valuable in an abstract sense. It represents decades of investment by specific people who built the instruments, who calibrated them, who analyzed their data, who publish papers about their findings. When an instrument goes dark, it takes a piece of that accumulated expertise with it. The 2023 antenna anomaly was particularly affecting for the team. When the signal was lost in late July of that year, the immediate response was methodical and professional. The team began diagnosing the problem, examining the available telemetry, constructing hypotheses about what might have occurred. But beneath this professional response was the awareness that the loss might be permanent. Voyager 1 was 23 billion kilometers away. The cause of the signal loss was unknown. The spacecraft was 46 years old, operating on declining power with aging systems. A catastrophic failure causing total and permanent loss of communication was not merely theoretical. It was a real possibility that the team had to hold in mind throughout the 2 weeks they worked to restore contact. When the recovery succeeded and the link was re-established in August 2023, the team's response combined professional satisfaction with genuine relief. The spacecraft was not gone. The mission would continue. But the experience had made concrete what had previously been an abstract awareness. Voyager 1 could go silent without warning at any time, and there would be nothing the team could do about it once the link was lost. The final goodbye, when it comes, will not necessarily announce itself in advance. This existential uncertainty shapes how the team approaches every operational decision. When considering whether to keep a marginally functional instrument operating or to shut it down to conserve power for other purposes, the calculus includes not just the scientific value of the data, but the knowledge that every measurement could be among the last. When reviewing whether to attempt a software upload to address a degraded capability or to leave well enough alone and avoid risking a new anomaly, the conservative choice has weight beyond mere caution. The spacecraft is not merely an asset to be optimized. For the people who have worked on it for years or decades, it has become something more complex than that, and managing its final years requires holding that complexity alongside the technical demands of the mission. What Voyager changed about how we understand the Sun. Before Voyager 1's interstellar transit, the heliosphere was understood primarily as a theoretical construct. Its existence was predicted from the physics of the solar wind and its interaction with the interstellar medium, and various indirect evidence supported the prediction. But no instrument had ever made direct measurements in the outer heliosphere, at the termination shock, in the heliosheath, or beyond the heliopause. The models that described the heliosphere's structure, its size, its shape, and its interaction with the interstellar medium were necessarily based on indirect measurements and theoretical assumptions rather than direct observation. Voyager 1's journey through the outer heliosphere and across the heliopause has directly tested and in many ways revised these models. The first major revision came at the termination shock, the boundary where the solar wind, travelling outward from the Sun at several hundred kilometres per second, abruptly slows to subsonic speeds as it encounters the back pressure of the surrounding interstellar medium. Models had predicted the termination shock would be located at approximately 85 to 95 astronomical units from the Sun. Voyager 1 crossed the termination shock in December 2004 at approximately 94 astronomical units, broadly consistent with predictions. But the details of the crossing revealed several unexpected features. The solar wind did not simply slow down smoothly at the termination shock. Instead, it underwent a complex deceleration with multiple structures suggesting turbulent behavior. The energetic particle environment at and near the termination shock was different from predictions. The magnetic field behaviour showed features that simple models had not anticipated. These discoveries required significant revision of termination shock models and led to a richer understanding of the microphysics of heliospheric boundaries. The heliosheath, the region between the termination shock and the heliopause, proved to be larger than most models had predicted. Voyager 1 took approximately 8 years to cross this region, from the termination shock crossing in 2004 to the heliopause crossing in 2012. This implies a heliosheath thickness of roughly 25 astronomical units, larger than the 10 to 20 astronomical units that many pre-crossing models had suggested. The heliosheath also proved to be more magnetically complex than anticipated, with the interplanetary magnetic field maintaining a sectored structure at greater distances from the Sun than models had predicted. The heliopause itself, as noted in Part 1, proved to be a sharper and more clearly defined boundary than many models predicted. The abruptness of the transition from solar-dominated to galactic-dominated plasma and magnetic field environments surprised many theorists, who had expected a more gradual transition zone. Understanding why the heliopause is as sharp as it is has required new theoretical work and has revised understanding of how heliospheric and interstellar magnetic field lines connect and disconnect at the boundary. Perhaps the most significant heliospheric discovery from Voyager 1's journey was the characterization of the asymmetric shape of the heliosphere. Before Voyager's crossings, the heliosphere was often depicted as roughly spherical, like a soap bubble, though some models had predicted it would be elongated in the direction of the Sun's motion through the interstellar medium, like a comet tail. Data from Voyager 1, combined with data from Voyager 2's crossing of the heliopause in 2018 at a different location in the heliosphere's southern hemisphere, revealed a heliosphere that is more compressed on the side facing the direction of the Sun's motion and more elongated on the downstream side. This asymmetry has important implications for the heliosphere's function as a shield against interstellar cosmic rays and for the interaction of interstellar neutral atoms with the heliospheric plasma. The direction of the heliosphere's asymmetry relative to the interstellar medium flow direction is now well established from the Voyager data, providing a benchmark that will inform models of how other stellar systems' astrospheres are shaped by their motion through the interstellar medium. Every piece of this understanding comes from Voyager 1's measurements, not from telescopes, not from remote sensing, from a direct in situ sampling of the environments in question, carried out by a spacecraft that has been operating continuously for 49 years. No other spacecraft has made these measurements. No other spacecraft currently planned will reach the outer heliosphere within the lifetimes of people currently working in the field. Voyager 1's dataset is unique not merely in its current state, but for the foreseeable future, which gives the continued operation of its remaining instruments a scientific urgency that goes beyond the value of any single measurement. The termination shock, a boundary. No one expected to cross. The termination shock is the first of the three major boundaries Voyager 1 crossed on its journey from the inner solar system to interstellar space, and its crossing in December 2004 represented the first time any human-made instrument had directly sampled this region. Understanding what the termination shock is and why its crossing was scientifically significant requires understanding the physical process that creates it. The solar wind flows outward from the Sun at supersonic speeds in all directions, carrying with it the Sun's magnetic field and a stream of charged particles, primarily consisting of protons and electrons. At the inner planets, the solar wind speed is approximately 400 to 800 kilometers per second. As it flows outward, it gradually slows, though still remaining supersonic at large distances. The solar wind cannot slow gradually and continuously all the way to zero, because the interstellar medium is pressing back against it with its own pressure. The solar wind eventually reaches the termination shock, where it undergoes an abrupt deceleration from supersonic to subsonic speeds in a manner analogous to the bow shock that forms in front of a supersonic aircraft. At the termination shock, the solar wind's kinetic energy is converted to thermal energy. The ordered directional flow of solar wind particles becomes a hot, turbulent, subsonic plasma. The temperature of the plasma in the heliosheath, the region between the termination shock and the heliopause, is much higher than the temperature of the solar wind itself because of this energy conversion. The heliosheath plasma is slower but hotter than the solar wind upstream of the termination shock. Models of the termination shock developed before Voyager's crossing made specific predictions about its properties: the location, the abruptness of the deceleration, the temperature increase across the boundary, the acceleration of energetic particles at the shock front, and the magnetic field behavior. Some of these predictions were confirmed, others were not. The most significant surprise was the behavior of the anomalous cosmic rays, high-energy particles that had long been suspected to originate at the termination shock. These particles, primarily protons and helium nuclei, were expected to be accelerated to high energies by the shock's electric field and should have shown increased flux immediately downstream of the shock. When Voyager 1 crossed the termination shock, the expected enhancement in anomalous cosmic ray flux was not observed. The flux actually changed relatively little across the crossing. This null result challenged the standard model of anomalous cosmic ray acceleration and suggested either that the termination shock was not the primary acceleration site or that the acceleration was occurring in a different sector of the termination shock than the one Voyager 1 sampled. Subsequent analysis, including data from Voyager 2's termination shock crossing in 2007, suggested that the termination shock is highly dynamic and non-uniform, with significant variations in its local properties depending on solar wind conditions at the time of crossing and on the local orientation of the magnetic field. Voyager 1 apparently crossed a quiet, weakly accelerating section of the termination shock, while other regions at other times may provide stronger particle acceleration. This finding revised understanding of how the heliosphere generates anomalous cosmic rays and opened new questions about the spatial and temporal variability of shock acceleration processes in space plasmas. The crossing also revealed that the magnetic field does not simply transition smoothly across the termination shock. Instead, the crossing involved multiple encounters with the shock boundary, suggesting that the termination shock was in motion at the time, likely moving inward and outward in response to solar wind pressure variations. These multiple crossings provided data on the structure and dynamics of the shock itself, information that was not available from any single, clean crossing. These detailed observations have had lasting effects on space plasma physics beyond heliospheric science. The termination shock is a relatively accessible example of a collisionless shock, a type of shock that plays important roles throughout the universe in settings ranging from supernova remnants to galaxy clusters. The physics governing particle acceleration at Voyager's termination shock crossing is related to the physics governing particle acceleration at much more energetic shocks elsewhere in the universe. Data from Voyager have been used to test and calibrate shock acceleration models that are applied across astrophysics. The pale blue dot, seen from the other side. On February 14, 1990, at the request of astronomer Carl Sagan, Voyager 1 turned its camera backward toward the inner solar system and photographed Earth from a distance of approximately 6 billion kilometers. The resulting image showed Earth as a pale blue dot occupying less than a single pixel in the frame, suspended in a sunbeam that was an optical artifact of the camera's design. Sagan's reflection on this image, delivered in a 1994 lecture and later published in his book of the same name, became one of the most widely quoted passages in the history of science communication. The cameras were turned off later that year, in April 1998, in a power conservation measure. This means that the pale blue dot image is the last photograph Voyager 1 took of Earth, and the perspective it represents, a view of the inner solar system from the outer solar system's edge, is the closest thing Voyager has produced to a view from the other side of the heliosphere looking in. The spacecraft is now much farther away, more than 160 astronomical units, rather than the 40 astronomical units of the pale blue dot image, but it carries no cameras to produce a corresponding image from this greater distance. The scientific and emotional significance of the pale blue dot image lies in the contrast it creates between the vast scale of space and the smallness of Earth within it. From 6 billion kilometres, Earth is not a world with oceans and continents and civilizations. It is a point of light, indistinguishable from the other points of light in the frame, except for its slightly blue colour and its position in the solar system. Sagan used this image as the centrepiece of a philosophical argument about the cosmic insignificance of the conflicts and pretensions that dominate human affairs, an argument that retains its force regardless of one's views on the specific political conclusions Sagan drew from it. Voyager 1's current position, more than 23 billion kilometres from Earth, represents a perspective more extreme than the pale blue dot by a factor of nearly 4. From this distance, Earth and the Sun are inseparable to any imaging system Voyager might carry. Both would appear as the same single bright point of light among all the other stars. The Sun, which from Earth appears to be 400,000 times brighter than the full moon, and which illuminates an entire hemisphere of Earth with enough energy to sustain the biosphere, would, from Voyager's current position, appear as a star of approximately magnitude -17 in terms of the standard astronomical brightness scale, extraordinarily bright by stellar standards, but point-like, no disk, no warmth, just a bright dot among thousands of others. From this perspective, all of human history, all human civilization, all the accumulated knowledge, technology, art, and experience of the species that built Voyager 1 is concentrated on or near that single bright dot. The spacecraft itself, the most distant artifact of that civilization, is approximately 0.025% of a light year from its origin. The nearest star other than the Sun is more than 170 times farther away. The centre of the galaxy is 26,000 times farther still. Voyager is not in any meaningful sense near anything except where it came from. This context, the context that Voyager's instruments provide for understanding humanity's place in the cosmos, is part of what gives the mission its significance beyond the specific scientific measurements it makes. The spacecraft is a physical demonstration of what it means to send something as far as physics currently allows, to maintain a connection across a distance that light requires 22 hours to cross, to receive data from a region of space that no human sense has ever directly experienced. The scientific results are real and important, but the mission also functions as an existence proof, evidence that a species that evolved on a rocky planet in an unremarkable stellar system can build something capable of crossing a boundary no material object had ever crossed before and reporting back from the other side. The image also carries a deeper scientific significance that has become more apparent with time. Every exoplanet discovered since the pale blue dot photograph was taken, every potentially habitable world identified by Kepler, TESS and the James Webb Space Telescope would appear similarly insignificant from a sufficiently great distance. The lesson of the image is not that Earth is uniquely small, but that planets in general are small. Worlds capable of supporting oceans, atmospheres, ecosystems, and technological civilizations occupy a tiny fraction of the volume of the universe. The overwhelming majority of space is empty. This reality helps explain why interstellar travel is so difficult. Voyager 1 represents the farthest any human-made object has ever traveled, yet in cosmic terms, it remains effectively in Earth's front yard. The spacecraft has crossed the heliopause and entered interstellar space, but it has not begun a meaningful journey toward another star. If the entire solar system were compressed to the size of a coin, the distance to the nearest star would still be measured in kilometres. The apparent closeness of the stars in the night sky is an illusion produced by perspective. The golden record attached to Voyager reflects this understanding. It was never expected that another civilization would realistically intercept the spacecraft. The probability is extraordinarily small. Instead, the record functions as a statement about humanity itself, a declaration that a technological species briefly existed around an ordinary star and chose to preserve a sample of its culture, science, music, languages, and images on an object destined to outlive every civilization that currently exists. Long after its final transmission, long after the Deep Space Network ceases tracking its position, Voyager 1 will continue moving through the galaxy carrying that record. It will remain one of the longest-lived artifacts humanity has ever created, a silent archive drifting among the stars. Whether it is ever discovered is almost irrelevant. Its existence demonstrates that a species confined to a single planet succeeded, however briefly, in reaching beyond it and leaving a durable trace of its presence in the wider universe. What no other mission has measured and why nothing will for decades. Voyager 1 is unique not merely in having reached the interstellar medium, but in having reached it with functioning instruments capable of making measurements. This distinction matters more than it might initially appear, because there are other spacecraft travelling through the outer solar system and beyond, none of which are making comparable measurements. Pioneer 10 and Pioneer 11, launched in 1972 and 1973 respectively, preceded Voyager 1 in the outer solar system, and both eventually crossed beyond the termination shock into the helio sheath. However, communication with Pioneer 10 was lost in 2003 at a distance of approximately 80 astronomical units before it had reached the termination shock, and with Pioneer 11 in 1995 at approximately 45 astronomical units deep in the outer heliosphere. Neither spacecraft carried instruments capable of making the specific measurements of plasma, magnetic field, and energetic particles that define the scientific legacy of the Voyager interstellar mission. Neither crossed the heliopause with functioning instruments. Neither has contributed data from the interstellar medium. New Horizons, launched in 2006 and famous for its 2015 flyby of Pluto, is currently travelling through the outer heliosphere at approximately 57 astronomical units from the Sun. It carries a suite of instruments capable of measuring some properties of its space environment. However, its instruments are optimised for the Pluto flyby and for the Kuiper Belt objects it has subsequently studied, not for the heliospheric and interstellar measurements that the Voyager instruments were designed to make. New Horizons' plasma science instrument, for example, has a different sensitivity and measurement range than Voyager's, and the comparison between the two datasets is not straightforward. New Horizons is not expected to reach the termination shock for perhaps another decade, and will not cross the heliopause for many decades after that, well beyond any reasonable projection of its operational lifetime. No other spacecraft is currently travelling in a direction or at a trajectory that would bring it to the heliopause in any near-future time frame. No mission currently under development or in the funded planning stages is intended to reach the heliopause within the next several decades. The proposed interstellar probe concept, which has received favourable consideration in NASA's decadal survey planning processes, would require new propulsion technology to reach interstellar space within a reasonable mission lifetime. And as of 2026, this concept remains in the development and advocacy phase, rather than the funded project phase. What this means in practice is that when Voyager 1's last instrument goes dark, the in situ measurement program of the local interstellar medium ends entirely. There is no replacement mission waiting. There is no planned successor. The dataset that Voyager 1 has been building since 2012, the first and so far only direct measurements of the plasma, magnetic field, and energetic particle environment in the local interstellar medium, will be complete when the spacecraft falls silent, and it will remain the sole dataset of its kind for at minimum several decades and possibly much longer. This creates a scientific situation that is unusual by the standards of modern astronomy, where most measurement programs have multiple platforms contributing to continuous data collection. The interstellar medium measurements from Voyager 1 are irreplaceable in a literal sense, They cannot be replicated, supplemented, or extended by any other currently existing or planned instrument. Scientists working with this data operate under the awareness that every year of continued operation adds measurements that cannot be obtained any other way, and that the end of the mission is also the end of direct measurement access to this environment for the foreseeable future. The implications extend beyond heliophysics. The local interstellar medium, the cloud of gas and dust within which the solar system currently resides, is the specific environment that shapes the heliosphere's properties and thereby influences the cosmic ray flux reaching Earth. Understanding the local interstellar medium is therefore relevant to understanding Earth's long-term radiation environment and its variation as the solar system moves through different regions of the galaxy over millions of years. Voyager's measurements provide ground truth that constrains models of how this environment has changed in the past and how it might change in the future. The Oort cloud Voyager will never see. Beyond the heliopause, beyond the region of interstellar medium that Voyager has so far sampled, lies the Oort cloud, the vast spherical reservoir of comets that is thought to extend from approximately 2,000 to as much as 100,000 astronomical units from the Sun. The Oort cloud is the origin of the long-period comets that occasionally sweep through the inner solar system, their orbits perturbed by the gravitational influence of passing stars or by the galactic tidal force. It represents the outermost gravitationally bound region of the solar system, the most remote territory over which the Sun's gravitational influence dominates. Voyager 1 is currently at approximately 160 astronomical units from the Sun, well inside the inner boundary of the Oort cloud. It will enter the Oort cloud in approximately 300 years and will take approximately 30,000 years to transit through it, before emerging on the far side at roughly 100,000 astronomical units, where the Sun's gravitational influence gives way entirely to the galactic environment. By any measure, this is an extraordinarily long journey through a region that contains an estimated trillion cometary nuclei, ranging from objects a few meters across to objects several tens of kilometers in diameter. But Voyager 1 will traverse the entire Oort cloud as a dead machine. Its final instrument will have gone silent in the late 2020s. Its transmitter will have fallen below detection threshold in the early 2030s at the latest. By the time the spacecraft enters the Oort cloud in roughly 300 years, it will have been dark for nearly 3 centuries. By the time it exits the Oort cloud in 30,000 years, it will have been silent for 30,000 years. The trillion comets of the Oort cloud, each one a primordial remnant from the formation of the solar system, will surround the spacecraft throughout this journey without the spacecraft being able to detect or report on any of them. The Oort cloud has never been directly observed. No spacecraft, no telescope, no measurement of any kind has provided direct evidence of individual Oort cloud objects. Its existence is inferred from the dynamical properties of long-period comets, whose near-parabolic orbits can be traced back to a reservoir at these distances, and from theoretical models of the solar system's formation that predict such a reservoir should exist. In principle, a spacecraft with functioning instruments passing through the Oort cloud would provide the first direct measurements of this region, potentially detecting the gravitational influence of nearby cometary nuclei, measuring the dust and gas environment produced by outgassing as comets are heated by distant starlight, and characterizing the radiation environment at this extreme distance from the Sun. Voyager 1 will pass through this scientifically extraordinary region without contributing a single measurement to human knowledge of it. This is not a criticism of the mission, whose operational life was never intended to extend to Oort cloud distances, and whose design was oriented entirely toward the planetary encounter phase and the interstellar medium mission that followed. It is simply a consequence of the mismatch between the spacecraft's operational lifetime, measured in decades, and the journey time to the Oort cloud, measured in centuries. No spacecraft designed to current technological specifications could be expected to operate for 300 years. The Oort cloud transit serves as a useful reminder of the scale of the solar system's outer extent relative to anything humanity has yet built or can currently plan to build. The spacecraft's silence on this journey does not diminish what it achieved during its operational years. It simply illustrates that the solar system extends far beyond what any single mission in its operational lifetime can explore. The contrast becomes even more striking when considered in terms of timescales. Human civilization, from the first cities to the present day, spans roughly 6,000 years. Voyager's transit through the Oort cloud alone will require approximately 5 times that duration. Entire civilizations could rise, transform, and disappear while the spacecraft drifts through a region of space that remains almost entirely unknown. The spacecraft's journey therefore highlights a fundamental mismatch between the timescales of human history and the scales of the solar system itself. If humanity still exists when Voyager enters the Oort cloud, the spacecraft will already be an artifact older than many ancient monuments are today. By the time it emerges from the cloud tens of thousands of years later, every language currently spoken on Earth will almost certainly have changed beyond recognition. Political systems, cultures, technologies, and perhaps even the biological form of humanity itself may be radically different. The civilization that launched Voyager will be as distant to those future observers as the builders of the first pyramids are to us, and likely much more so. The Oort cloud also represents a frontier that future exploration may eventually reach. Unlike the planets and moons visited by 20th century spacecraft, the Oort cloud remains almost completely unexplored. It contains material that has been preserved since the earliest stages of solar system formation, frozen at extreme distances where sunlight is little more than a bright star. These objects are time capsules from an era more than 4.5 billion years ago, preserving information about the chemical and dynamical conditions that existed when the Sun and planets were forming. A dedicated Oort cloud mission could reveal details of solar system history unavailable anywhere else. Yet the distances involved ensure that such exploration remains a challenge for future generations. Even spacecraft far faster than Voyager would require decades or centuries to reach substantial portions of the cloud. The outer solar system is not merely large by human standards, it is large even by the standards of modern space exploration. In that sense, Voyager's future path through the Oort cloud is symbolic. The spacecraft will travel through one of the richest unexplored regions associated with our Sun while remaining unable to observe it, a silent witness moving through a realm humanity has inferred but never directly seen. Its trajectory reminds us that exploration is not limited by curiosity, but by time. The solar system is vast enough that even our greatest journeys have only begun to reveal its true extent. What remains after the signal fades? When Voyager 1 finally goes silent, the silence will be preceded by a period of gradual fading. The transmitter, operating at approximately 23 watts of radio frequency power, requires a minimum electrical input to maintain the power level necessary for the signal to be detectable at Earth. As the RTG output continues to decline, the transmitter will eventually be receiving insufficient power to maintain this minimum level. The signal will weaken before it disappears entirely, becoming progressively more difficult to detect against the background noise of the cosmos and the thermal noise of the Deep Space Network's receiver electronics. The engineering team at JPL will monitor this fading carefully, adjusting signal processing parameters to extract the maximum information from the weakening transmission, scheduling additional tracking time on the 70-meter antennas to compensate for the reduced signal strength, and documenting the final measurements with the care that befits the end of a 50-year mission. The last packets of data will be processed, archived, and added to the comprehensive Voyager dataset that will remain available to researchers for decades after the mission ends. There will likely not be a dramatic final transmission, a last message composed by the mission team and sent into the void. The spacecraft does not have the capability for that kind of scripted finale. The signal will simply fade below the detection threshold, and the last data received will be whatever the spacecraft happened to be measuring in its final operational minutes. The team will spend some period after the last detected signal attempting to confirm that the loss is permanent rather than a temporary anomaly, as occurred in 2023 when the antenna briefly pointed away from Earth. Eventually, after no further contact is established, the mission will be officially closed. What follows is not nothing. The Voyager 1 dataset, accumulated over 49 or more years, will continue to be scientifically productive for years, decades, and possibly longer. In the history of space science, many of the most significant scientific results from a mission are published not during its operational phase, but years after its conclusion, when researchers have had time to develop the theoretical frameworks needed to interpret the data fully, to compare the measurements with data from subsequent missions, and to identify patterns and correlations that were not apparent in the immediate context of data acquisition. Voyager's data has already demonstrated this scientific longevity. Many of the most cited papers using Voyager data were published decades after the planetary encounters, as new analytical methods allowed researchers to extract additional information from the original measurements. The interstellar medium dataset, which is newer and in some ways more challenging to interpret because there is no prior comparable dataset to provide context, will likely support scientific research for longer than any single current researcher's career. The physical spacecraft, meanwhile, will continue its permanent motion through the interstellar medium. By the time the signal fades, it will be somewhere around 24 to 25 billion kilometers from Earth, or roughly 160 to 165 astronomical units. It will continue moving outward at approximately 17 kilometers per second. The RTGs will continue producing heat at declining levels, eventually reaching a state where the thermal output is negligible. The spacecraft structure will slowly equilibrate to the temperature of the surrounding interstellar medium, a process that will take centuries because of the thermal mass of the metal structure and the insulting properties of the MLI blankets that will still be wrapped around the spacecraft. In tens of thousands of years, the spacecraft's temperature will have fully equilibrated to the interstellar medium. The MLI blankets will still be intact, reflective surfaces unaltered by the vacuum and the trace radiation of interstellar space. The aluminum structure will be unchanged, protected from any chemical weathering by the absence of reactive gas. The gold-plated copper record will be as it was when it left Earth, perhaps slightly abraded on its outer surface by micrometeorite impacts, but structurally sound and still carrying its encoded sounds and images of Earth. The spacecraft will be, in some meaningful sense, a message, not a deliberate message crafted with hope of reception, though the golden record serves that function symbolically. But a message in the sense that its existence proves something, that a civilization arose on a rocky planet orbiting a minor star in the outer arm of a spiral galaxy. That this civilization developed sufficient understanding of physics and engineering to build a machine capable of leaving its home stellar system, and that this civilization valued knowledge enough to invest decades of effort in maintaining contact with something 23 billion kilometers away across a vacuum so empty that the speed of light requires nearly a full day to cross it. The message will travel for geological timescales, carrying the fingerprint of its origin in its design, its materials, its trajectory. No civilization that might one day encounter it could fail to recognize it as an artifact. Whether any civilization will ever encounter it is another question entirely, one to which the honest answer is almost certainly no. The interstellar void is very large and the spacecraft is very small, and the trajectory it follows will not pass close to any star for tens of thousands of years. And when it does pass close, the distance will still be measured in light years. But the spacecraft does not require reception to mean what it means. It means what it means because it exists, because it was built, because it flew, because it kept flying for 49 years while the people who built it aged and retired and died, and were succeeded by people who kept listening. The culture of Voyager and why it matters. No account of Voyager 1's survival is complete without acknowledging the cultural dimension of the mission, the way it has occupied a specific place in human self-understanding that goes beyond its scientific measurements and its engineering achievements. Voyager has become something more than a spacecraft. It has become a symbol, and understanding what it symbolizes reveals something about what the act of exploration means to the civilization that undertook it. The Golden Record is the most explicit expression of this cultural dimension. Carl Sagan and his collaborators did not include it on Voyager primarily for scientific reasons. The probability that the record would ever be found by an extraterrestrial civilization was acknowledged to be extremely small. The record was included because the act of deciding what to include, of curating a portrait of Earth for an unknown audience, was itself meaningful. It forced a moment of collective reflection. What are we? What matters to us? What would we want someone to know about us if they could know only one thing? The answers encoded on the record, music, languages, images of nature and humanity, the sounds of a living planet, are a portrait of what the people who made it valued at that specific moment in human history. This cultural function of exploration, the way it generates self-knowledge through the attempt to explain oneself to an imagined other, is not unique to the Golden Record. It pervades the entire Voyager mission. The images of Jupiter's volcanic moon Io, of Saturn's intricate ring system, of Uranus's tortured moon Miranda, of Neptune's unexpected geysers on Triton. Each of these discoveries changed not just scientific understanding, but human self-understanding. They expanded the known range of what is possible in a planetary system. They revealed that the solar system is stranger and richer and more diverse than any prior model had suggested. They demonstrated that the universe is not a place that conforms to human expectations, but a place that consistently exceeds them. The sustained 49-year maintenance of the connection between Earth and Voyager 1 is itself a cultural achievement. Maintaining any complex technical system for 49 years requires institutional continuity, dedicated expertise, and a consistent prioritization of the mission's value over the many competing demands on institutional attention and resources. In the 49 years since Voyager 1's launch, human civilization has experienced the personal computer revolution, the internet revolution, the transformation of telecommunications, the end of the Cold War, the rise and transformation of the European Union, wars, economic crises, and social changes that have altered nearly every aspect of daily life. Through all of this, the Voyager mission team has persisted, maintaining contact with a spacecraft that has been receding from Earth at 17 kilometers per second for longer than most of the world's currently operating institutions have existed in their current forms. What does it mean for a civilization to keep listening to something for half a century? It means that civilization values continuity, that it recognizes obligations to projects begun before the current participants were born, and that it understands knowledge to be worth pursuing even when the immediate practical return is limited. These are not self-evident values. They compete with immediate practical demands for resources and attention, and they often lose. The fact that Voyager has continued for 49 years, surviving budget pressures and institutional changes, and the succession of generations in its management team is evidence of something real about the civilization that built it. The final end of the mission will not diminish this. The scientific data will remain. The cultural achievement will remain. The spacecraft itself will remain, moving through the interstellar medium indefinitely. What will end is the conversation, the daily transmission of data across 23 billion kilometers, the evidence that something built by humans is out there still speaking, still connected to where it came from across a distance that defies easy comprehension. The engineers who will receive the last signal from Voyager 1, whenever that moment comes, will be the inheritors of a chain of technical expertise and institutional commitment stretching back to 1977. They will almost certainly not have met the people who designed the spacecraft. They may have grown up reading about its discoveries in science textbooks. They will have built their professional lives around maintaining contact with a machine they never saw on Earth. When the last signal fades, they will experience something that has no precise precedent in human exploration: the permanent, unrecoverable, final end of contact with something that is not gone, that will still be out there, still moving, still carrying its golden record through the galaxy, but silent. The silence will be the last message from Voyager 1, not a message encoded in bits or transmitted on a radio frequency, a different kind of message carried in the sudden absence of something that had been present for half a century. A message that says, we went as far as we could, we listened as long as we could, we learned what we could learn, and now the physics has taken over and the distance has won, and the spacecraft goes on without us into the dark, 1 degree above absolute zero. The answer to the question of how Voyager 1 has survived 49 years without freezing is a physics answer. The cold of deep space is not aggressive in the way that terrestrial cold is aggressive. It does not attack through molecular contact. It waits for heat to radiate away through the only mechanism available in a vacuum, and it does so slowly enough that a machine generating its own heat through the steady decay of radioactive plutonium wrapped in insulating blankets that reflect that heat back into the spacecraft can maintain its operational temperatures for decades. The RTGs provide the heat. The multi-layer insulation retains it. The engineering decisions made in the early 1970s balance these two forces precisely enough that the balance has held for longer than anyone could guarantee. But the physics answer is not the whole answer. The whole answer includes the engineers who kept the mission running through budget pressures and generational change and aging systems and a 2023 anomaly that could have ended everything. It includes the scientists who found new things to discover in an environment no instrument had ever sampled, and who published papers based on data from a machine that launched before they were born. It includes the cultural weight the mission has carried as an expression of what humans value enough to pursue across 49 years and 23 billion kilometers. And it includes the spacecraft itself, which has not frozen, which has not stopped, which is still out there, still moving at 17 kilometers per second through the interstellar medium that no other human instrument has ever directly sampled, carrying everything that was put into it, into a future that none of its builders will live to see. The cold of deep space is 1 degree above absolute zero. It has been waiting for 49 years. It is still waiting, and Voyager 1 is still warm.